These are the notes for Standard 3.5, which is solving problems using Newton's second law and kinematics. So, as a reminder, we've been focusing on these equations here during this unit about forces. And in the last standard, we utilized the F net equation, which allowed us to calculate a net force with mass and acceleration, or calculate an acceleration with net force and mass. Now we're going to also be considering these motion equations that we used in Standard 2, which help us relate position, velocity, time, and acceleration. And it's important to keep in mind that these equations are linked by acceleration. And so you'll see that in our two example problems today, we can either use motion problems to calculate acceleration and then use that acceleration to calculate forces, or use forces to calculate a net force and an acceleration, and then use that acceleration in these motion equations over here. So in our first example, we have a 70 kilogram person who uses a lift in order to accelerate to a height of 5 meters in 8 seconds. We have to calculate the forces acting on the person. So we'll start by making a force diagram, and we can see because this person is accelerating upwards, we need to have a larger upwards force than we do a downwards force. To calculate the gravitational force, we can use our equation mass times acceleration due to gravity, and we get 70 times 9.8, or 686 newtons, pulling this person down. In order to figure out how large the normal force is, we can't just say that it's equal to the gravitational force. It needs to be bigger, and how much it's bigger by is based on the net force. So if we can calculate the net force, we can then calculate the normal force. But in calculating the net force, we need the acceleration, and the acceleration isn't given in this problem. So what we need to do is we need to consider a motion equation. Here we know that the person is going to have a final position of 5. We know how long it's going to take them, and we know that they're starting on the ground and they're starting not moving. So we can use this equation, then plug in those values and solve for the acceleration, which will be 0.16 meters per second squared upwards. And so by using this motion equation, we were able to find what the acceleration of the person has to be. And then we can take that acceleration, we can plug it into our net force equation, and then we can find that the net force is 10.9 newtons, meaning that the normal force upwards needs to be 10.9 newtons stronger than the downwards force, meaning that the normal force acting on the person from the lift has to be 696.9 newtons in order to accelerate that person 5 meters in 8 seconds. For our second example, we have a shopper that's pushing a 20 kilogram cart at 1 meter per second on a surface with a 0.25 coefficient of friction, and then they let go. We have to determine how far the cart will travel before it stops. And so the force diagram for this cart is, since the person has let go, we don't have any force pushing the cart in the direction that it's moving, even though the cart right now is moving to the right, and then it's experiencing friction, which is going to slow it down. As we look at this force diagram, we can assume that the vertical forces are balanced because the cart isn't accelerating upwards or downwards, but the horizontal forces are unbalanced. We have a friction force acting on the cart to the left, but we don't have any force pushing on the cart to the right anymore because the shopper has let go. So we can calculate the gravitational force being 196 newtons. We can say the normal force is equal to that gravitational force. And then we can calculate the friction force by multiplying the coefficient of friction times the normal force. And we get that the friction force is 49 newtons. So we have a fully calculated force diagram, but this question isn't asking about the force diagram. It's actually asking about how far the cart will travel, which is a displacement. So at this point, it might be good to start the d-guess method and draw a diagram of our situation. We have the cart moving at 1 meter per second at the beginning and then not moving at the end, and we need to figure out how far did it move. So looking at our initial velocity, our final velocity, and the displacement that we do not know, the equation that comes to mind is this one, since no mention of time is made in the problem at all, and this equation doesn't rely on time. But there's another thing that we don't know, which is the acceleration of the cart. And so that's where we're going to use our force diagram in order to calculate that acceleration, so that then we can in turn calculate the displacement. So our net force is equal to the mass of the cart times the acceleration of the cart. And we know that the F net of the cart is this friction force, since that is the unbalanced force in the horizontal direction. That there's 49 more newtons pushing on this cart to the left than there is pushing it to the right. And so we can plug in the net force, we can plug in the mass of the cart, and then we can solve for the acceleration. Notice that the acceleration of the cart is in the same direction as the net force. And then we can use this acceleration and the velocities given in the problem. Notice that the initial velocity, which is 1 meter per second, is positive since it's moving to the right. And then our acceleration is negative since the acceleration was opposite the initial velocity. We can then simplify this equation a little bit, move the 1 to the other side, and then divide both sides by negative 4.45, which gives us an answer of 0.22 meters. And it's a positive answer, which means that the cart is going to move 0.22 meters or 22 centimeters to the right before it stops.